Conservation of angular momentum. Angular momentum is conserved in a body even if the distribution of mass changes. When ice skaters spin, they start with their mass as far out as possible from the pivot point, something like this. As they draw in their arms, their moment of inertia reduces, and so, as their angular momentum is constant, their angular velocity must increase. Let's look at that in symbols. Angular momentum is equal to moment of inertia multiplied by angular velocity. So angular velocity equals angular momentum divided by moment of inertia. So, as the moment of inertia I reduces, angular velocity omega must increase. If a large star is rotating, if gravity causes it to reduce in size, it will spin faster. Here's an example. A skater starts a spin with arms and one leg out to the sides, giving her a moment of inertia of 95 kg-meters squared and an angular velocity of 10 radians per second. When she draws her arms and leg in, her moment of inertia reduces to 55 kg-meters squared. What is her new angular velocity? Well, angular momentum at the start is given by I omega, where I is the moment of inertia and omega the angular velocity. Putting the values in gives an angular momentum of 950 kg-meters squared radians per second. The final angular velocity will be given by omega equals angular momentum over moment of inertia. Putting in the values gives an angular velocity of 17.3 radians per second. In this short video, you can see conservation of angular momentum in action. When the rider's mass is close to the pivot point, they have a small moment of inertia and a high angular velocity. When the mass is further from the pivot point, they have a higher moment of inertia and a lower angular velocity. So here they're travelling quickly, much more slowly, quickly again, slowly, quickly, slowly, and even slower.